Ladies and gentlemen, welcome to the Materials Week, organized as a part of European City of Science Katowice 2024. This event is co-organized by the Faculty of Materials Engineering at Tydzień University of Technology. Our today's guest is Professor Hirpa Lemu from the University of Stavanger, Norway. Professor Lemu will present a lecture entitled Exploring Potentials of Modern Materials Realizing Sustainable Additive Manufacturing. We warmly invite you to listen to the presentation.
Thank you for inviting me to make this talk in relation with the European City of Science 2024 action at Katowice. I am Hirpa Lemu, Professor of Mechanical Design Engineering at University of Stavanger, Department of Mechanical and Structural Engineering and Material Science. And it is my pleasure to continue our collaboration with Stavanger University, which we had already some contacts and some visits. And I hope this also will be a contribution to the collaboration. And upon the invitation, then I entitled my talk as Exploring Potentials of Modern Materials in Realizing Sustainable Manufacturing. And this is also to find common denominator between the goal in the invitation and my research activities, which is mainly on additive manufacturing. Then before proceeding with my talk, then let me present first the content of my presentation. The first part is introducing myself, in particular my research activities, and then give a brief presentation of the university where I am working, University of Stavanger. And then I will focus on my main talk on additive manufacturing research, especially focusing on materials for sustainable manufacturing. My academic profile, as you see, looks like this. And as academician, one of my obligations, of course, I know that it is generating funds for research activity. Then in the collaborations, research applications, fund applications, and so on. So far, I have generated around 30+ million Norwegian kroner. And these funds are used, of course, in collaboration with other institutions, as well as recruiting researchers and so on. By using funds from the Norwegian government, from the research funds, and so on, so far I have graduated 8 PhD students. And currently, there are 10 active PhD candidates. 2 of them will be graduated early next year. And also, I have been involved beyond teaching, also in supervision and of bachelor and master thesis students. And this resulted in more than 60 students graduated in masters and more than 200 students graduated in with bachelor degree. And my publication records, together with my students, my colleagues, and the like, show that I've been involved as a sole author and co-author of journal articles and articles in proceedings and so on, is over 250. And have also been organizing conference here at University of Stavanger, entitled CoTech. It is about computational methods in or computational technologies in engineering, particularly in offshore and ocean engineering related activities. And the conference is intended to invite researchers in the area and come to Stavanger and share their expertise and so on. And so far we have organized 4 and the conference is organized every other year since 2017. And one of the researchers' profile nowadays is as an indicator is the Google Scholar profile. Then my Google Scholar profile shows as it's given here, and it's interesting to see also the trend that it is progressively increasing index, which indicates also to what extent me and my team are actively publishing and sharing the knowledge for the outside public. Then my research area, in particular, of course, as a mechanical engineer, the mechanical engineer is very wide and it covers a lot of areas. But the current hot topic that we are working on is in additive manufacturing and streamline technology. And then there are research going on, both for master thesis and PhD thesis on design for additive fabrication, topology optimization, additive manufacturing, especially for healthcare application, powder bed fusion based additive manufacturing of metal printing, and also wide arc additive manufacturing technology. And for several years back, then we have been also involved in simulation-driven design optimization for improved performance of energy converters, such as gas turbine and water turbine, modeling and analysis of material entropy, study of advanced composite materials, and also modeling and simulation of mechanical systems and energy converters, converting machines are some of the research focus areas that we have been involved with. And yeah, I am from University of Stavanger, and Stavanger is located at southwest part of Norway. As you see, this is a Norwegian map. And the university is located just in front of the North Sea, as you see here. And it is located also at a very interesting area because the Stavanger is known, it is known for its offshore industry in the North Sea. Because of that, the university's focus or our engineering focus is mainly in design and materials engineering. That represents the core part of our research. And at the same time also collaborating with the oil industry in the region is also one input for our research activities. And the university has more than 12,000 students. Among these, over 1,000 are international students. And there are also 1,900 employees. And the university's activities are also, or the teaching and research activities are divided into 34 bachelor programs, 43 master programs, and 8 PhD programs. And structurally, the university is divided into 6 faculties. And then the Faculty of Science and Technology is where I am working. Then the other faculties are Faculty of Social Sciences, Faculty of Arts and Education, Faculty of Health Sciences, Faculty of Performing Arts, and Business School. And among the faculties, of course, the Faculty of Science and Technology is the largest and the core part. And it is divided into 7 departments. And then our department, there is a Department of Mechanical and Structural Engineering, the Material Science, and the others are both science and in particular energy related. In particular, the core part of the faculty is related with energy and petroleum engineering and energy resources. The others we can consider as supporting disciplines, both from science and technology and economy and so on. Then we have Department of Chemistry, Biosciences and Environmental Engineering, Department of Ethical Engineering and Computer Science, and also Department of Mathematics and Physics and Department of Safety economics, and planning. So these are the departments that are operating under the Faculty of Science and Technology. And if I come to our department, the academic profile of our department is that it has full-time scientific staff of 20. And we have also professor tools. That is, the professor tools are people who are working in the industry and involved in our teaching and supervision to share their experience. And we have also engineers or laboratory staffs of about 20, and research fellows or PhD students, which is more or less dynamic. From time to time, new candidates come, and some existing ones are graduated. Anyway, on average, we have around 20 PhD students. And the postdoctoral researchers, also it is varying, but we have in average 4 candidates actively working. And the total students, bachelor and master at the department level, is 660. Having this short presentation of myself and my university, then let me go to the core part of my presentation or my talk. Then I will start from where I defined my research focuses in additive manufacturing or AM. Then I decided to focus on the application of the technology and the design for additive manufacturing, because the design methods and the documentation of the design in the conventional way and the additive manufacturing way is different. And then the other part, and which is the core part of our discussion or my talk here, is about the materials and the processes. So I will not go particularly in the applications and the design for manufacturing, but I focus on materials and processes related with the additive manufacturing research. Then let us begin from the beginning, I would say. And even though the additive fabrication of different forms existed for many years, then the most the modern element of the additive manufacturing or 3D printing started in the mid-1980s, especially the person who is often mentioned as the father of this technology is Charles Hull, who invented the stereolithography apparatus technology in 1984. And then it has he has managed to process or to convert the 3D computerized model to a physical object. That was the intention. And then in the academic area, there's always a question whether this invention, in a way, of Charles Hull's is really a new technology, because technologies can be modified, can be converted in another form, or can be combined, and so on. Then what Charles Hull did was somehow understanding the existing technologies and combined the available ones to get a new technology. And then there are 3 main existing technologies that are combined in the solutions of the stereolithography apparatus, or SLA. First, what Charles Hull try to understand is how to command machines using a computerized numerical control. And such controls for machine tools were developed in the 1950s, 1960s, based on the advances into computer technology, advances in the microelectronics, and so on. And also, in addition, in the 1980s, the 3D modeling and combined this is one cornerstone. The other one is, how can we transform materials from one form to other, from solid to liquid, and so on. Then the possibilities that exist in the laser technology and other physical principles. And the third part is, of course, and the important part is material science and technical chemistry. Then by combining these three, then Charles Hull came up with the concept of stereolithography apparatus, which we call SLA process. Then the technology proceeded with different forms of different technologies appeared in the market nowadays. They can be in the hundreds, and FDM, SLS, and so on. They are the offsprings of the initial idea of from stereolithography, I would say. Then before going further, probably it might be good to distinguish between additive manufacturing and the conventional manufacturing process. And it is positioned as a manufacturing process for green transformation. And if I make just a short comparison between the conventional one and the additive, in the conventional part process, for example, if I want to produce a part which looks like this one, then I have to start from the top, then remove the first piece or the first chip and go down. And based on the achievable depths of cut, and then go down until I remove this material, and this removed material will be a chip. In the case of additive manufacturing, in the contrary, then the process starts from the bottom, and materials are deposited layer by layer until the final layer is achieved. Then in that process, then there is no or very minor waste, which goes to as a chip. For example, in this case, as we see, if to get this object, we can start from input material, which looks like this, then remove the materials to get the shape, and the removed material is the chip. Then we have the waste here. But in the case of additive manufacturing, we can start from a powder, metal powder, or other form of the input material. Then it is melted and deposited and layer by layer. And as it is, we can see that the scrap or the waste material can be comparatively, can be as small as this one compared with the conventional processing. That is the reason that we can advocate that additive manufacturing is, it leads to a more green manufacturing process, and it is a technology of that contributes to the green transformation. There are, of course, different engineering materials, and some of them are polymers are one of them, metals, composites, ceramics, and biological materials are nowadays appearing also as engineering materials. And the American Society for Testing and Materials, ASTM, has already standardized 7 major material processing categories. That means we can process materials by binder jetting, by direct energy deposition, by material jetting, by material extrusion, by using powder bed fusion, polymerization, and sheet lamination. Then the material processing for additive manufacturing purpose can be one of these standardized processes. Then, as it is indicated here, a study back in 2016, the UK indicates the landscape of this technology and how the maturity level of these materials. Then it puts the materials, and it indicates that polymers are the most commercial available materials for additive manufacturing. They are only not yet developed for direct energy deposition at that time and sheet lamination. And metals are metals and composites are more or less at similar maturity level at that time, but there were also some works in the research and development phase for metals, such as metal jetting possibilities, metal extrusions, and sheet laminations, and so on. So metals also are promising materials for sufficient maturity for additive manufacturing. And the others, the composites, ceramics, and biological materials were at a different level of maturity at that time, but the situation can be different now. In general, polymer materials are the most developed due to the ease of manufacturing or ease of processing. And a 2020 report from AMFG about AM landscape indicates also that materials represent 20% of the AM's landscape, which indicates the influence of materials in terms of sustainability and also green transformation and so on. Then that is a significant contribution in the process. And as I mentioned already, the objective of Charles Hull when he developed the stereotypography apparatus was how to use this technology for rapid prototyping. Then different technologies appeared in the market. Then the idea of transforming from prototyping to fabrication of functional parts emerged due to the maturity of the technology. And even in our house or in our teaching and research activity, we started to focus on this as a design modeler or as a prototyping tool back in 2008 and bought this machine. Then around 2015-16, then we observed that there is this transition is going to be the reality. Then we got this FDM machine, which was known to be a commercial functional part fabrication machine, and conduct research on that. And then also the last couple of years also we have been working on the SLM, which is a metal printer. And then our focus has been first design for additive manufacturing. For example, what we see here is a spray nozzle with different sealings and O-rings and so on, suffering with leakage. Then by using the design for additive manufacturing concept, then that has been simplified in the design of this form. And the other focus area that we worked on is material characterization, then which materials and what type of processing, which parameters of printing, how can we control it, and so on, have been our focus, and especially on the material characterization and the process control. Apart from the common engineering materials or engineering products, of course, this technology has shown significant impact in other areas such as in medicine. Then long back we understood that there are different images generated in medicine where doctors are taking CT scans, MRI images, and so on. And of course, the interest to use this technology in the medicine has also developed. And we know already, if we have a 3D CAD model of our organ or any part, then there is a sufficient developed technology to build it layer by layer. Then the challenge is now, how can we convert this medical image data to a understandable format that the 3D printer can understand? Then that we identified as one of the challenges to transform from medical image data to a 3D CAD model, mechanical drawing type of data. Then after observing that, okay, that can be printed, if that transformation can be done, then what material can we print and can perform in the way that it can be part of our organ, then can it perform, say, our leg or whatsoever, then that is another challenge to understand the material process, how it can be processed. So generally, acquisition of the 3D image data is one, and segmentation, that means identifying and highlighting the area of interest, and then converting the data into a printable or processable format, and then printing by selecting proper material. And one research that we are currently working on that is for the healthcare devices, which involves materials and applications, particularly reverse engineering of engineered or natural part, and then involving also multi-material printing to combine different materials. And in this research, we collaborate with hospitals, especially with orthopedics doctors. Then by receiving medical image data, then converting that to the printable part, then we can print by selecting materials that are suitable or compatible for that purpose. Then that has also led us to the concept of bioprinting for our future research. Another research that we have ongoing is 3D printing of polymers on functional textiles. And that is also one interesting topic that we are working, because such monsters, which are complex geometry, then we wanted to use the design freedom that this technology provides. And one of the work is, of course, to produce filaments by combining with the already existing polymer materials. Then we can combine other materials in order to achieve the required properties, and also to make additional properties such as conductivity, rigidity, so selected regions, or mounting of additional devices such as sensors, decorations, and studying the property. For example, if it is a textile, then it is washability, to what extent it is a binding effect, and so on are the focuses in this research. Then optimizing the printing parameters accordingly. And another research is on laser powder bed fusion technology. Then we selected aluminum powder. Of course, that's only because of availability for the existing 3D printing process. Then the work involves studying the influence of process parameters, such as influence of printing strategies and building orientation, and in order to study the performance, and then also developing the property prediction models using machine learning methods. And the other technology or research that we are conducting is additive manufacturing. This is a form of welding process. Then the research is done on Inconel 625 material. Then the study focuses on process optimization to reduce defects, because, as I said, it is a sort of welding process. Then there are many defects as porosities, roughness issues, and also residual stresses and so on. And then we wanted to study the influence of the process parameters, how the parameters influence, and which parameters influence, in particular, residual stresses, strengths, hardnesses, and so on. And then also developing thermomechanical model to predict the behavior for the other parameters as well, so that it can be easily simulated and predicted. Another interesting part of the research, of course, is what this technology provides us is flexibility, so that we can use locally available resources. Then in our research, we work on producing filaments from natural fibers. And this research is being conducted in Ethiopia. from plants by extracting natural fibers from different plants. For the moment, it is we are limited to insect or false banana plant, which is this type of plant, and then what is called sisal plant. The reason is that locally, traditionally, the fibers from these plants are used by farmers or for different purposes. Then why not? We use them for as filament in 3D printing. And one reason is, of course, these fibers or these plants are abundantly available. And secondly, they are biodegradable. Then if we combine with existing polymer materials, then we can reduce the impact of polymer materials to the nature, to the sustainability of the environment, and we can reduce the damage that the polymer materials can bring to the manufacturing industry. And then we conduct a study of the mechanical properties after printing with the extracted or produced filaments. And the other part is, of course, recycling of filaments from waste materials. Then we had some collaboration with a recycling station here. Then by producing filaments, then also study the filament properties for the different types of plastic materials, then print them, and then also study the behavior of the printed parts, their effect is whether they are difficult to print, then shrinkage effect is, and so on. So and we have conducted some research, but it is something that we will continue with. Then to summarize this talk, AM-based manufacturing of products can have some key environmental and sustainability advantage from the materials perspective. At least we can mention 3 key advantages. One is reduced raw material requirements. That means less need to mining and refining basic materials. As already illustrated, we can use locally available natural materials and combine with polymers and so on, then we can reduce the impact of the existing material types that we used to use. And the second one is reduce the dependence on energy intensive and inefficient material processing, such as casting and so on. And then the third one is developing products with enhanced performance. That means less compromise for design complexities, so that we can design a very complex geometry without any compromise we can produce. Then AM realizes through design optimization. That means materials are used only where needed, and optimized material utilization and energy consumption contributes to the green transition or transformation that is sought. And AM opens also opportunities to new and modern materials, including utilization of biodegradable materials. Yeah, that is the end of my talk, and thanks for your attention, and thank you again also for the invitation.